Welcome to Calculus for Economics, everyone. Today is Friday, April 3rd, and I wanted to do just kind of a little workshop on problem solving with compound interest. We had seen the basics of compound interest in our previous lecture, and then we had a little video showing how you can look at comparing investments using the idea of the effective interest rate. But there's just a host of different kinds of problems that are can be involved with compound interest and problems of practical interest, like how long would it take my investment to double given a certain interest rate, or what interest rate do I need in order to get an investment to perform at a certain level. So I wanted to take a look at several different problems and kind of show you, I think, a general technique that can help you work through lots of different kinds of problems here. So let's jump into it. The key idea that's going to be behind all these is just the compound interest formula. The accumulated rate, the accumulated amount, is the principal value, the principal amount times 1 plus the nominal rate divided by the compounding frequency, and then all that raised to the m times t power, where t is the time in years. So let's see how this formula really can work in different ways to get us to answers of various kinds of problems. The first kind of problem I want to consider is one about what rate is it going to take in order for a certain kind of performance to result. So let's take a look. Here's a problem of that sort. Suppose John has $5,000 to invest, and he'd like his investment to grow to $6,000 in a period of 3 years. What interest rate does he need in order for this to happen? And we're told to assume monthly compounding. So here you can imagine someone with a chunk of change to invest, and they're trying to shop around to meet a certain goal. So how can we use our knowledge of compound interest to inform us on this problem? So the first thing you want to do is just identify in the problem the values that you have and relate them to that compound interest formula. So in this case, our principal is 5,000, and the amount we want, an accumulated amount that's desired, is the 6,000, and we desire that after a time of 3 years. And because we're told to assume monthly compounding, the compounding frequency m is 12. So that's key right there, just identifying what you got from the problem itself, and then plug that into the basic compound interest formula. And so you just see me doing that here, replacing the values in the formula with the values that I know, and what's left over is that interest rate. So somehow I should be able to solve this equation now for the interest rate, and that's precisely what is asked for in the problem, right? What interest rate does he need in order for this accumulation to happen? So let's see how we would do that. And in this process, you're basically going to be using properties of exponentials and logs in order to solve an equation. So the first thing I'm going to do is divide both sides of this thing by 5,000. So I'll get 6,000 over 5,000 on the left-hand side, and I'm just left with the 1 plus r over 12 to the 36 power. That's just the 12 times 3 here on the right-hand side. I'm trying to solve for r. So if I raise both sides to the 1 over 36 power, I'll get closer to that solution, that goal, right? Raise the left-hand side to the 1 over 36 power, you get 6/5 to the 1 over 36. Raise the right-hand side here to the 1 over 36 power, and use a property of exponents, and you wind up just getting 1 plus r to the 12th. What we were using there is really the property that x to the m power raised to the n power is just x to the m times n. And here my x was the 1 plus r over 12. M was 1 over, M was 36, and I raised all of that to the 1 over 36 power. So the powers multiply in that case, and you just get 36 times 1 over 6, or 1 plus r over 12 to the first power. And now we can solve that equation easily. Just subtract 1 for both sides, then multiply by 12. And so you get r is 12 times the quantity, 6/5 to the 1 over 36 minus 1. And just grinding that out on a calculator gives you 0.06093. Here I've rounded to 4 significant places, right? And that means 4 places after the decimal point. I'm sorry, after all the leading zeros. So this really went on for quite a few digits, and I'm just rounding. Starting at the 6, I take 4 places, so I rounded that last digit there. And by the way, WebAssign, I think, will usually want interest rates as a percentage. So the 0.06093 would translate into 6.093%. So John here needs a 6.093% interest rate to have that $5,000 principal accumulate to a $6,000 amount over 3 years in this situation. Another kind of problem that you see quite a bit is, well, okay, I've got an investment. How long is it going to take that investment to grow to a certain amount? So let's take a look at a problem here. Suppose Amy deposits $20,000 into a savings account that pays 2% interest compounded weekly. How long will it take for her initial investment to grow to $25,000? Well, let's begin as we did before by just accumulating the information that we know, right? So what's given in this problem? Well, Amy has a principal of $20,000. The account pays 2% interest, so my R is 0.02. The compounding is weekly, so the compounding frequency, that's the number of compounding periods per year, would be 52. And the amount she wants is $25,000. So let's plug those values now into the compound interest equation. There we get it. And the only thing that's not known here is t. So again, the idea is going to be to take this equation and solve it for the unknown quantity t. So I'll start out as I did before by dividing both sides by 20,000 and simplifying that a little bit. So you get 25 over 20. And then I get, on the right-hand side, I just have the 1 plus 0.02 over 52 to the 52 times t. Now, I'm trying to solve for t, and t is in the exponent here. So there's a little bit different solution here, or solution technique. When your variable's in the exponent, typically what you want to do is take the logarithm of both sides. And I'm just going to use the natural logarithm because that's the simplest one to work with generally. So if I take the logarithm of both sides, I get the log of 5/4. I just reduce 25 over 20 to lowest terms. That's 5/4. And if you take the log of the right-hand side and use that property of logs that says log of a base to a power is the power times the log of the base, you get this expression. So log of 5/4 would be 52 times t plus natural log of the base, which is 1 plus 0.02 over 52. And now I can solve that for t, but essentially by just dividing. I divide by 52 times this natural log of 1 plus 0.02 over 52, and I get t is the natural log of 5/4 divided by the whole quantity, 52 times the natural log of 1 plus 0.0252. And then just grind that out on your calculator again, and you get 11.159 and some change. Again, I'm going to round things to 4 places here, so I'm going to report this result as 11.1593. And the units here are years because in our compound interest formula, time is always in units of years. So one thing you can see here is that solving problems like this is you're going to need to know and be able to use those properties of exponents and logarithms that we talked about a few lessons prior when we were doing those things. So that's really important. Um, Here's another problem, kind of another how long problem. Suppose you have an investment that pays 4% annual interest, compounded daily in this case. How long does it take for an initial investment to double? So let's collect what we know. First of all, we've got an investment that pays 4% annual interest. It's compounded daily, so the number of compounding periods per year is 365. And then we're asked, how long does it take for an initial investment to double? So it's a little off putting at first, maybe, that we're not given an actual amount for an initial investment. Uh, but we can still work through the problem because when we talk about an initial investment doubling, that means the accumulated amount ought to be twice the initial amount, the principal. So what we know here is that A equals 2 times P. Uh, and now we can plug those things into, again, just the basic compound interest formula. My A is 2P, my P is unknown, but then I have 1 plus the interest rate over the compounding frequency, and then times compounding frequency times time. And so we need to solve this equation for t. Remember, t is in the exponent again, so we'll probably be using logarithms, and you can see that we will. But first, let's clean things up a bit. We can just divide both sides by p, or cancel the p's if you want to think about it that way. And you get 2 equals 1 plus 0.04 over 365, the quantity raised to the 365 times t power. Trying to solve for t, so I'm going to take logarithms now. Log of 2 would be, remember I'm taking the log of a base raised to a power, so log of that would be the power times the log of the base. And now we can solve for t as before. Divide by 365 times the logarithm here, and so t would be natural log of 2 divided by 365 times the natural log of 1 plus 0.04 over 365. If you grind that out on a calculator, you get about 17.3 years. And so in this situation, if you've got an interest rate of 4% compounded daily, it's going to take about 17.3 years for your money to double. That may seem like a long time, but let me give you a little bit of advice for free. When you start a retirement account, which you should do as soon as you can, as soon as you start working for sure, and contribute to it. But that 17 years is not a super long time compared to your working lifespan. And so you can expect to have at least a couple of doublings along the way in a retirement account just from the compound interest that's going on. And that would be in addition to any in a retirement account, you're going to be adding new deposits all the time, which we're not even considering here. So your retirement account can double in much less than 17 years if you just keep it in there, and if you let the compound interest do its magic, and also keep your contributions going. Of course, I guess I ought to add a caveat at this point. There's always going to be times when the stock market goes down, like it has recently. I've been paying into my own retirement account for many decades now, and yeah, I've lost a little money over the last few weeks, but I haven't withdrawn anything, and and I've been through these kind of things before. We had a stock market dip in 2008 because of the Great Recession. There was one in 2001 because of the dot-com bubble. There was one in 1989. There was one in the early 80s. This kind of thing is nothing to run panicky from. Just slow and steady will build your retirement in a very good way. Okay, a third kind of problem that you'll see is a problem called present value. The basic idea here is, suppose that your rich uncle tells you that hey, in 20 years I'm going to leave you $1 million. That's good to know, right? And suppose he's absolutely honest and 100% reliable, and suppose that's going to happen. How much is that that $1 million 20 years in the future? How much is that worth right now, today? That's the idea of present value. And the key idea there is that $1 million 20 years into the future is not worth $1 million today. Because why would that be? Well, setting aside all sort of risk of, market downturns or your uncle, giving it to somebody else because he changed his mind, setting all that aside, if I wanted $1 million 20 years from now, I wouldn't need to lay down $1 million today and bury it in the backyard. I could invest a smaller amount. I don't know, maybe 700,000, maybe something like. Actually, probably less than that. We saw that the doubling time for a 4% investment is around 17 years. So if I just laid down $500,000 today and let it accumulate interest at 4% compounded like we were doing before, I would have over $1 million in 20 years. So that says the present value of $1 million 20 years out in the future is going to be less than $1 million. And the whole idea of present value computations is to make that precise. So let's consider this problem. What is the present value of a $50,000 promissory note due in 10 years? So this means somebody's promised to pay you $50,000 in 10 years. Let's assume an interest rate of 3% compounded quarterly. And of course, we're going to ignore any sort of shocks that would invalidate the promissory note. We're going to assume the promise is ironclad. Well, the basic idea here is again just the compound interest formula. Let's tally up what we know. This $50,000 is not a principal anymore. From the point of view of its present value, that $50,000 is the accumulated amount. Because remember, if I want $50,000 10 years from now, I could put a principal of less than $50,000 in some investment and just have it accumulate up to the point where I get $50,000 in 10 years. So in a present value problem, the amount in the future is the accumulated amount, not the principal amount. In fact, the principal amount will be the present value. We'll see that in a second. What else do we know? We know the time period here is 10 years, the interest rate is 3%, and the compounding is quarterly, so the compounding frequency is 4 for compounding periods per year. Same formula, plug in what we know. Now we're going to be trying to solve for P, right? So the principal in a present value problem is really the present value. And so I'm just doing that here. I plugged in what I know, and then to solve for P, I just need to divide by this exponential expression on both sides. Remember, dividing by a factor is the same as multiplying by 1 over that factor, and 1 over a factor is that factor raised to the negative power. So dividing by this thing to the 40th power is the same as multiplying by this thing to the negative 40th power. And it winds up that present value is $37,082 and some change. So the present value of $50,000 10 years in the future is about $37,000, assuming an interest rate of 3% compounded quarterly. So the basic formula that underlies all of this is that compound interest formula. The book does present a separate formula for present value, but I just want to point out that it's really just this formula with this factor 1 plus r over m to the mt carried over, divided by on both sides. So really, the present value formula is just the same as the compound interest formula, or just a quick derivation from it. So, with these kind of examples, you should be able to do the homework that'll be posted shortly. It'll be due Monday night. As always, let me know if you have questions or if circumstances are preventing you from handing in a homework on time. I can always consider an extension there. In the meantime, y'all take care and have a good weekend, and I will see you again soon. Bye for now.